Hello, in this short video I would like to show how I would have solved the first and last and one and only online assessment in our electrical engineering course, because this course just runs over one semester, so there's just one online assessment. So I will open it up, and what I've also prepared here is Octave that I will use as a kind of powerful calculator to do some number crunching, and I have my drawing pad here. So if I would like to do some sketches, reformulate some equations, do stuff like this, then this will be very handy. So as a student, you would have 1 hour and 30 minutes or 90 minutes in total to do this test. I hopefully will do it in something like 30 minutes. So let's start. And take a look at the first task. We have two resistors. The values are given here, and at these terminals we have a direct current of this value. And now the question is, what is the current flow through this resistor here? And the circuit schematic looks a bit strange, to be honest, because you might think that these two resistors are in series. They are not. This is a parallel connection. So we can use the current divider rule, and I will write a short Octave script. Copy the values 2.8 and 9.3 ohm, and the total current is 577 milliampere, which is 10 to the power of -3. And so then we can use the current divider rule. So the resistance in the other branch divided by the total resistance of this mesh, and then multiplied with the total current. And so this is current divider. And so now we get some result, and this result should be entered here in milliampere. So I will set the comma. I'm not sure. I think even if this is English here, I have my language settings to German. So I need to use a decimal comma instead of a dot. And this is the right answer. So let's continue with the next question. Okay, same schematic. What is the current flow through the first resistor? So I can just copy this equation here, change this 2 into a 1 and this 1 into a 2, and it should be this. And so then this should be the current converted into milliampere. Okay, that's also correct. So next question. We have some ohmic inductive load consisting of a resistor and some inductance in the following interconnection. This might also a little bit look like these two elements are connected in parallel, but as you can see, they are connected in series. And we have some active power and reactive power given, and a source voltage that is used to operate this circuit at a certain frequency. And so now the question is, what is the effective value of the voltage drop across the inductor? So across this element here. So let's use the new script, start with clear all, take all the values. So the active power is this in watt, the reactive power is 63, voltage, total voltage is 176, and the frequency is 48 Hertz. And so now we can calculate the voltage drop across the inductor here by using a voltage divider rule. And for this we would need to have XL, the value of, or the reactance of this inductor. And for this we need to have the inductance and maybe the angular frequency, which is 2 times P times F. And then this divided by the total impedance of the circuit, and this multiplied with the total voltage. So this would be one way to do it. I mean, the other way would be to say Yeah, so maybe we can do it this way. And we need a couple of other values to do this. So at first I would calculate apparent power, and apparent power in this case is the square root of the sum of the active power squared and the reactive power squared. And from S and V, we can calculate the current. So the current is S divided by the voltage. And so if we have current and voltage, we can calculate this impedance, which is voltage divided by current. Okay, so then the last thing that we need to know is this reactance of the inductor. And this is somehow related to our reactive power here, because reactive power is current squared, and the current we have already calculated times XL. So from this I can calculate XL, and this should be the reactive power divided by the current squared. Okay, so this should be it. So I will call this RL, and then we can see, okay, we get this as the angular frequency. This somehow makes sense. 180 volt ampere for the apparent power, approximately 1 ampere of current. Then this is the impedance, this is the reactance, which somehow makes sense, and then we get 61 volt across this inductor, which also somehow makes sense if we have a total voltage of this, and if we have approximately, let's say, 3 times more active power, real power, than this reactive power. So this seems to be correct, and I can check the result here, and this is correct. Okay, so next page. Same question. What is the apparent resistance magnitude of the complex impedance in ohm? This is what we have already calculated here. 171. Okay, this is correct. Next page. We have a diode, and this diode has some forward voltage and some operating current, and should be operated on a voltage source with a certain value. And to limit the current, a resistor is connected after the diode, right downstream of the diode, which is referred to here as a trailing resistor. And how much or how large, how much resistance needs this trailing resistance? So new type of task, new script. I will copy the values. This is 3. The current is 11 milliampere. And the source voltage is 11.3 volt. And so then we can calculate the voltage drop at the resistor, which is the difference of the source voltage and the voltage drop across the diode. And the resistor itself is then the voltage drop across the resistance divided by the current. So this is trailing diode, no, trailing resistor. Yeah, and this is the value, and this should be specified in kilo ohms. So I need to move the comma by 3 decimals, and that should be it. And yeah, at the end, it of course does not matter if the series resistance to limit the current, if it's before the diode or after the diode. This is maybe to confuse large language models that might be helpful or not helpful in solving such tasks. Okay, this is the right answer at least. So then we have 2 capacitors that are connected in series, and the total capacitance, one capacitance is this, and the total capacitance of the series connection is this. And how large is the second capacitor, C2? So the equation that you need here is that the total capacitance, or 1 over the total capacitance, is the same as 1 over the first individual capacitance plus 1 over the second individual capacitance. So if we would like to have this, we need to take this minus this and 1 over this. So let's have a new script and once again start with some clear all and say C1 is 3.3 micro and C total is 0.8 microfarad. And then C2 is 1 over 1 divided by C total minus 1 divided by C1. And that should be it. So this is the capacitor. And here's the result. 1 point something microfarad. And this also seems reasonable because the calculation here is the same as for the parallel connection of resistors. And so if you have 3 ohm and 1 ohm in parallel, the total resistance could be something like 0.8 ohm. Okay, so that's correct. We continue with the 7th question. And a new type of task. We have some circuit schematic that has the shape of a triangle, also not very common, maybe also to confuse large language models because it does not fit to the usual training material. And we would like to do nodal voltage analysis. So we have 3 nodes. This is what is marked as the reference node, and then there are 2 remaining nodes, 1 and 2. And there are 3 resistors and 3 current sources. The values are given here. And the system of equations then for this nodal voltage analysis looks like this. And what we would like to know now is what is the entry G11 in this nodal conductance matrix here. And so I will use a new script and copy the values. So R1 is 1.3 ohm, R2 is 2.2 ohm, and R3 is 3.7 ohm. And the first source current is 1.4 ampere, the second source current is 2.1 ampere, and the last source current is 3.2 ampere. And so now the G11, this entry here on the main diagonal of this matrix, is the sum of the conductances of the resistors that are connected to this node. So this should be 1 over R1 plus 1 over R2 because the resistors 1 and 2 are the ones that are connected to this node. So that should be it. This is nodal voltage analysis. And this is the result in Siemens. And now we would like to have it in millisiemens. So we need to move the decimal comma to this place and check, and that's the right answer. So let's continue with the next one. We once again have the interconnection of these 2 resistors. Here it also looks like they are in series, but they are in parallel. And it's the same values that we had before here for our current divider. And so now the question is, what is the total resistance? And the total resistance is this parallel resistance, or the equivalent resistance of this parallel circuit. So this can be calculated as the product of the 2 resistances divided by the sum. And if I run the script, then this also makes sense. 2.1 something ohm for this parallel resistance or resistance of the parallel circuit. Okay, so here we have same the same schematic, the voltage is asked for. Voltage is resistance times current. And we get 1.2 something volt, which also makes sense with the values that we calculated before. Then we have another question related to this nodal voltage analysis. What is the value of the entry 1, 2, I22 in the vector of the source currents? And this is always the sum of the current sources connected to the respective node. So at the second node we have IS2, which is flowing towards the node, and IS3, which is flowing away from the node. So minus IS3, and then we get some negative current there, minus 1.1 ampere. This should be also specified in ampere here. So this is correct, this looks good. Next page, we once again have this RL circuit. And now the question is, what is the power factor of the load? And this power factor can be easily calculated. Cosine phi is the real power or the active power divided by the apparent power. And this should be our power factor. This also is reasonable because we have much more active power than reactive power, so it's kind of close to 1. Okay, that's correct. So next question, once again related to this diode circuit. And here the question is, what is the electrical power that is dissipated in this resistor? So let's check for the resistor here. And the power is voltage multiplied with current. And this is the power in watt, and we would like to have it in the unit milliwatt. So I will copy this, paste here, set the decimal comma, and that's the right answer. Okay, next page and next question is once again related to this nodal voltage analysis, and similar question, what is the entry, the first entry in this vector of source currents? So we need to have a look at the first node, and here this current source is flowing towards the node, this current source is flowing away from the node, so we need to have this minus this and calculate, get some value, minus 0.7. Of course, you could also calculate it from here, right? 1.4 minus 2.1 is minus 0.7. And that's the right answer. Okay, so next page, we once again have this ohmic inductive load. And now the question is, what is the apparent power? That is something that we also already had calculated. So it should be this value in volt ampere. Makes sense. Okay. So the next question is also related to this schematic here. What is the effective value of the voltage drop across the resistor? And this should be also specified in volt. So we can use the same voltage divider rule here and change V into VR into VL, and no, this was somehow wrong. And then we need to have the resistance, and the resistance is something that we can get from the active power, because active power is current squared multiplied with resistance. So in the same way like this, we can calculate the resistance, which is power divided by current squared. And so then we get the voltage drop across the resistor. If we do a quick check and say voltage drop across the resistor squared plus voltage drop across the inductor squared, take the square root of this, we should get the total voltage. And this is also the case, so this is probably correct. 164.9 in this case. So check, and that's the right answer. Next question. And we have half of the questions already. What is the reactance of the inductance? And this is something that we had also already calculated. 59.99, or I could probably also just enter 60. And that's the right answer. Then there's another question related to this diode circuit. What is the efficiency of the circuit, assuming that all electrical power in a diode is converted into visible light? So we need to have the power at the diode, and this would be the voltage at the diode multiplied with the current. And then we can say, okay, it's the power dissipated or converted in the diode divided by the total power, and the total power is the power in the diode plus the power in the resistor. And so we get 26.55% if we convert this into percent. And of course we could have also just calculated the diode voltage divided by the source voltage. Should be the very same factor, because this is, let's say, the useful voltage divided by the total voltage. So let's check, and this is correct. So next page. We have once again the circuit with the two resistors that once again somehow look like a series connection, but as you can see, it's a parallel connection. And the question is, what is the total power that is dissipated in both of these resistors? So this was, I think, this script here, and the total power can be calculated from the total voltage, or from the voltage and the total current. And then we get this value in watt, and we would like to have it in milliwatt. So we need to shift the comma once again by 3 places, and that's the right answer. Next question. The diode circuit. What is the electrical power dissipated in the diode? We had already calculated this here, 33 milliwatt. Okay. Next page. What is the power P1 dissipated in the first resistor? So this is what we can get from the current in the first resistor multiplied with the voltage. And so we get 550.7 milliwatt. This is also the smaller resistor, so the smaller resistor has more current and therefore more power, and that's right. Then we have another question related to this nodal voltage analysis. The question is, what is the entry G22 in this nodal conductance matrix? So this was this script, and G22, the entry on the main diagonal can be calculated from the sum of the conductances of the resistors that are connected to this node. And these are the resistors R2 and R3. So this should be it, because it should be given once again in millisiemens. So let's check. That's the right answer. Next question. What is the resistance of this load? I think this is also something that we had already calculated. 160.9. Okay. Then same circuit. This also looks like maybe a parallel connection, but of course it's a series connection. How large is the phase angle, the argument of the complex impedance of the load? And this should be given in degree. So if we have resistance and inductance already, or no, resistance and reactance, of course we could write down a complex impedance and say this is resistance plus J multiplied with the reactance. And then we can calculate the angle, the phase of this complex impedance, and multiply with 180 divided by P. And this would be, let's say, phi z, the phase angle of the impedance. And this is the value here, 20.4 degree. And we should get the same, for example, if we calculate the Arcus tangents of QL divided by P, reactive power divided by the real power. Was not QL, it was just Q. And of course, this then also needs to be multiplied with 180 divided by P. Okay, we get the very same value. So let's check, and this is correct. So next question, once again related to our current divider. What is the second power? So second power can be calculated from the second current. And we get 165, and this also makes sense because power 1, now quick check, plus power 2 should give the total power, and this is the case. So 0.8. So let's check. This is correct. 25th question. Once again related to the diode, what is the remaining voltage drop across the resistor? I think we had already calculated this. This was this VR, just the difference. 11.3 minus 3 is 8.3, so this is also correct. And another question related to the nodal voltage analysis. What is this entry here in the equation? And this is the coupling conductance between node 1 and 2. And this is minus 1 over this resistance. The resistance that is connected between the two nodes. So this should be this value here, and we need to convert from Siemens into millisiemens. So shift the comma a little bit by 3 places, and that's the right answer, and it should be negative, of course. So next page, what is the effective value of the current through this load? This was this script, so run it once again. We had already calculated the current, and the current was a little more than 1 ampere in this case. So that's correct. What is the inductance of the load? So this XL that we used here is omega times L, angular frequency, times the inductance. So we can calculate the inductance by using this reactance and divide by omega. And we get 0.19 Henry, and this should be specified or converted into millihenry. So it should be approximately 200 millihenry. And this is also correct. So we have the second to last question. Two uncoupled inductors, L1 and L2, are connected in parallel. And the first inductance is this, the total inductance is this. How large is the second inductor then? And inductors in parallel can be calculated with the same equation as this one here. So I will just use this script and save it as inductor and change all the C's into L's. And except for this, it should be the very same equation. And I just need to change the values. So the second one is 2.8 milli and the total one is 1.2 millihenry. And let's calculate. And so then the total, the second inductance should be 2.1. Quick check if we have 2.8 and 2.1 in parallel. Total inductance could be 1.2, something like this. This makes sense. So let's check. And this is right. And so we have finally the last question. And the last question is, what is the entry G21 in this matrix? And I think we already had calculated G12 and G21 is the same. So we need to have this minus, here's the comma to specify this in millisiemens. And then this is the right answer. So this is looking not too bad, right? All answers correct. I will close this trial and then you can see some overview. And if, I could also submit, but probably this task had the right amount of difficulty, not too easy, not too complicated, at least for some students that just finished one semester of electrical engineering. As a quick check, if you have properly understood and if you have developed some competencies in doing these basic circuit calculations, I think this was just the right amount of difficulty in this task. And now I would be also super interested in how large language models like ChatGPT, Gemini, Claude, or maybe this quite new DeepSeek will perform in solving these tasks, as I've already tried the corresponding German online assessment with ChatGPT and Gemini. I will probably just test this one here against Claude of Anthropic and DeepSeek.